episode of Klingberg Wing Mark II Development. I'm Rolf Klingberg, your host. Today you find me kneeling next to the cockpit mock-up. I haven't mentioned this online, but I haven't really talked about it in any detail. I'm going to do a little bit of that today, and later on we'll have another video, more details on the cockpit area. This is pretty close to what it's going to be for the final configuration. This section here is 2 feet wide, final one's 30 inches wide. And then it has a framework underneath it, pilot's cage, for handling the glider on the ground. There are some significant differences in this design compared to aircraft such as the Swift. Then I thought I'd talk about them here a little bit. I'm going to actually be making some tubing for this pilot's cage in the video today. And I thought that a little preview of the cockpit area would help you understand what I'm making. I'm actually going to make a piece of tubing to go back here on the pilot's cage. All of the PVC that you see here is actually composite tubing on the real thing, and it's set up like a parallelogram so that when you pull the pin here, the whole thing can fold up flat for easy transportation. So you have a center section of the wing and the pilot's cage stay together as a unit. The tubes that you see here, the final configuration will actually be cables. There's going to be a little tail boom back here and cables going back this way to stabilize it. It'll be actually lighter weight than the tubing. All of the tubing will be made in using the same methodology that I've demonstrated elsewhere on the channel here, with the exception of the front portion of the cockpit. This curved portion will actually be made pretty much like this one is here. There's a wood core with foam shaping and some nice twill carbon fiber that wraps easy around shapes like that. This will be a nice rigid structure that holds the width of the pilot's cage. This bar is not actually in the final configuration. It was done just for the mock-up to keep it all in one piece. You see a axle-like thing here. I originally had a wheel up front. I've eliminated that concept. There's actually going to be a skid up front, a little spring-loaded skid to absorb any potential dropping of the nose. I'm sure we've all done that once or twice landing. You trip, drop the nose. Got to have something to absorb that impact. That'll be that skid. So I'm probably going to run a rigid piece of tubing, half-inch, from here up to this bracket also to absorb those types of impacts. Nominally, people will support the pilot on the pilot's cage, and of course that seems to make sense. You know, you put a harness or a sling here, and the pilot sits, and the loads are applied to these fore and aft pieces of tubing, and those loads are transferred up into the airframe via the uprights. That's all well and good. I've decided to go down a different path of attaching the pilot directly to the wing itself. That is pretty traditional with when you're using weight shift. Of course, this glider is going to have elevators, but I want the pilot to be able to move to adjust the CG for high-speed flight and low-speed flight. So I want the pilot to have the ability to move easily, and I'm going to suspend them from the wing itself. Now, that provides several advantages on the design. Number one, I can probably cut the weight of the entire pilot's cage in half. And that's on the order of 3, 4, 5 pounds of weight that I can leave out by having the tubes be quite lightweight. If you're not having to carry the pilot loads up to the framework, then you can make this tubing much lighter because you really only have to deal with ground handling loads, perhaps landing loads, and just general durability of assembly and disassembly. So I'm going to be able to go a lot lighter on the pilot's frame. There's going to be a lightweight harness like a mountaineering harness for paragliding, those very slim, lightweight ones for supporting the pilot. We don't need a harness that has the reserve parachute capability because that's going to be a ballistic chute will be up inside the wing here. There's a couple other reasons for suspending the pilot from the wing itself. Well, actually, I've given you two already. There's a third one. shift your weight back and forth for high and low speed flight. Number 2, make the pilot's cage a lot lighter by running the load straight from the pilot up to the wing. And number 3 is a thing called pecking. Pecking is a high frequency dipping of the nose like this at certain speeds and flight conditions. I'm going to do a video later that goes into the aerodynamic details about why pecking occurs, and I believe I have a solution for that, and part of the solution is suspending the pilot from the wing itself rather than the pilot's cage. So you'll be able to look forward to an interesting yet very speculative approach about resolving the pecking issue. It's pretty common on a lot of flying wings. Not all of them have it. My first wing did, but many do, and I believe I have a solution for it. So the pilot's cage is actually attached to, this is one of the actual flight hardware ribs. It'll be inside here, and there's brackets that will be attached to the rib here, extend down just like you see here, that provide an attachment point for the tubing at the top. There'll be a carbon fiber reinforcement here and a little standoff so that the brackets are the proper width. This will just be carbon fiber plate and be fine. So that the attachments here and here, and it transfers the loads of the pilot's cage up into the structure of the wing via the brackets that are here. For the pilot suspension, the rib is much stronger. I have this one here. This is flight hardware. It's carbon fiber on both sides. And this is going to have a relatively long bracket on the back here that sticks down. Going to be on both sides and come together like this for the pilot hook in. You can hook in at different locations depending upon your weight and how you like to set the CG. What you don't see on the ribs yet are the cap strips. There's pull-truded carbon fiber cap strips that are going to go on here all the way around. They carry the bending loads from the pilot. So this is up inside the wing. The skins are on it. There's cap strips. There's a tube up front, and the pilot is literally suspended back here. If you look elsewhere on the channel, you'll see where I've tested this particular type of rib and support structure, make sure that it's strong enough for the application. And I just thought that I'd show you a little bit of flight hardware here as we move forward. So in a moment here, I'm going to turn stuff around. I'm going to point you in the other direction, and we're going to talk a little bit about how I'm going to make this tubing, and then I'm going to fast forward and you'll watch me make the tubing. So stand by for 1 second. Okay, here we are facing the other direction. As you can see, I'm set up to make tubing. Behind me I have an 1.25" diameter piece of aluminum tubing mounted in my tubing production jig. It's been prepped with plastic and mold release, ready to go. And I got my table covered with a butcher paper with the plastic side up. If you watch the other videos, you know why I do that. I'm going to wet out the cloth here, roll it up, and transfer it over to the tube. And I do that for a lot of different assemblies because when you lift it up, it leaves the excess resin behind, and that helps hold down the resin content of the components that I'm making, which is always a challenge with hand layups. So you see here fabric for making a piece of tubing that is 4 layers thick for part of the pilot's cage, and you'll see that I have Kevlar and carbon fiber. The Kevlar that I have here is 120 cloth. It's 1.7 ounces per square yard. It's beautiful, smooth, fine fabric, quite popular in the aerospace industry for a variety of parts. Here I have standard 3K toe unidirectional carbon fiber, and they are the same width, and when I make this part they'll be stacked on top of each other like this, and you can easily see that as soon as I begin to roll this, you're going to get a tube that has alternating layers of Kevlar and carbon fiber, just like that. It's going to be carbon fiber, Kevlar, carbon fiber, Kevlar. The outside surface is Kevlar. The reason for that is safety. If you've ever broken a piece of carbon fiber, especially tubing, it is, well, like a weapon. It's really a spear. The ends can be very sharp. Shards will fly off that are sharp as needles. In a crash, it could definitely be a deadly weapon. When you wrap it in Kevlar, you've essentially put a bulletproof vest around the carbon fiber, and hold those shards together, and it doesn't fail in the same way. As a matter of fact, because of the dissimilar nature of the two materials, rather than just getting a catastrophic explosion type failure, which is how carbon fiber fails, you'll actually get some delamination first, the carbon fibers will be breaking inside the matrix, and the Kevlar is still holding together, and you just get kind of a mushy part. Now that means that the part actually fails prematurely. If it were all carbon fiber, it would actually fail at a higher load level. But we can adjust for that just by making the tubing just a little bit thicker, maybe one extra layer of cloth. I used this on my first glider. I know it works great. I'm going to be making this in two versions though. You're going to watch the first part here is going to be just straight alternating layers of Kevlar and carbon fiber, and I'll cure that, take it off, and I'll bring you back later when I make a second version. Since my first glider, I've created this method of the sandwich panel style tubing. You can find that video elsewhere on the channel. And I'm actually going to do a layup where I have one layer of Kevlar, one layer of carbon fiber. Actually, the carbon fiber will be on the inside, then Kevlar. And then I'm going to wrap that with very thin Aerex foam, and then have two layers on the outside. One of Kevlar, one of carbon fiber, such that the Kevlar is on the outside. So in this version, we'll have 4 layers of Kevlar, 4 layers of carbon fiber. In the sandwich panel version, half that number. 2 layers of Kevlar, 2 layers of carbon fiber. So we'll be cutting the weight in half on the composite fabric, which means that we cut the weight of the resin in half, almost. There's resin that goes into the foam, that adds a little bit back in. So the tubing's not quite half the weight, but close. And I'm going to make 2 samples, same length, and I'm hoping I can use both of them on the glider somewhere. If not, that's okay. I'll just make more tubing, but I'll be able to test them. I'll be able to rig them up and put a load on the ends of them and see what the bending stiffness is like for each piece of tubing, and weigh them and get some type of idea of the bending stiffness versus weight for the 2 types of tubing. Once I have that testing done, then I'll make a decision as to how I want to make the tubing for the rest of the pilot's cage, whether it's going to be just straight tubing or the sandwich panel style tubing. So I'm going to run you on fast forward here. You're going to
like a bird on a tree. I'm just sitting here, I got time. It's clear to see.
Hey, welcome back. I thought I'd do something a little different this time and do some lessons learned in the middle of the video. Usually I keep those lessons learned till the end, but I had some events occur here that justify a change in format. This is the tube that you just watched me produce. It came out okay. It's extremely strong. Probably a little stronger than it needs to be. The wall thickness came out right about 40 thousandths. Probably drop that down to 30 thousandths. This is 4 layers thick, alternating 4 layers Kevlar with 4 layers unidirectional graphite. Excuse me. Probably drop that down to 3 layers. Anyway, the weight of the tube came out at 1.7 ounces per foot, which means that the pilot's cage is about 20 feet of tubing, 20 plus a little, so we're looking at 20 ounces and another 3/4, another 15, so 35, 36 ounces just for the tubing, which is several pounds. It doesn't sound too bad, but I can actually probably take, a half a pound out of that, and a half a pound would be great if I could get it out of the pilot's cage, put it somewhere else, because you've got all the fittings to do, the bolts, you name it. There's going to be a lot of accoutrement on the pilot's cage that's going to add to the weight. Now, in watching the fast forward portion of the video, you may have noticed that I struggled a bit making this tube. I had problems with the Kevlar staying aligned with the unidirectional carbon fiber. I haven't had that problem in the past. I've made many of these tubes and I experienced new problems this time around, and that caused me to struggle. And as I look at this tube, I see what appear to be micro voids where resin did not fill the fabric properly. The tube is plenty strong. I don't think that these little voids would be a problem. I don't know if the voids are on the inside or if it's just this outer layer. I have no idea. No way for me to tell for sure. If I took this out for an expensive ultrasound test, we'd probably get a look at that, but I don't plan on spending that money. Here's what I noticed was the difference from the tubes that I made in the past. This is the fabric that I used to make this tube right here, this unidirectional. Now you notice that it has scrim on this side, which are these white fibers, and it has scrim on this side. And this scrim runs on a diagonal and on the 090. And then it's got this little zigzag scrim on the back side. You could call it the front side, but it seems to be the back side. I've not worked with unidirectional carbon fiber with this much scrim on it before. And I think that's what caused the problems. Scrim, my understanding was it wets out well with the resin. I'm using a low viscosity resin, but that's where the little voids are, where these crossovers are on the scrim. And these are very stiff here. They feel almost like nylon, although they should be fiberglass. And they just didn't take up the resin. They didn't blend together. Maybe this is really meant for autoclave process where you have really high pressures and you can push that resin in there. Although my shrink wrap did work quite well on the tube. Shrink wrap came down, took the temperature up in the oven, and excess resin had dripped out of the seams. So this tube on resin fabric ratio is pretty much right on the money. So I don't know for sure. Now, this is the carbon fiber I've used in the past for making the tubes. This carbon fiber comes from TAP Plastics. This carbon fiber came from Aircraft Spruce and Specialty. And look at the difference here. There's almost no scrim in the TAP Plastics unidirectional carbon fiber. Very fine fibers, I feel, at the edge here, and it's interwoven in between. It's not just glued on the outside. In fact, on neither side can you really see that scrim that's holding it together. Now, that does mean that if you're not careful with the fabric, it can come apart quite easily like this, whereas the stuff from Aircraft Spruce, much stronger in that direction. You got to pull harder to break that scrim. This fabric from TAP Plastics never had a problem with this, rolls up much nicer. So I'm going to make another one of these tubes. I'm going to make another 3-footer out of this remaining piece of scrap that I have from TAP Plastics. and I'm going to make 3 layers thick because that's a 12-inch wide piece of cloth, and that's what this cloth comes in. How convenient. And we're going to flip the screen around. I'm going to come back, and we're going to compare the 2 tubes. So hang in there, and I think we're all about to learn something together. So I'll be back in just a moment. Okay, I'm back. Only been a moment for you, been a couple of days for me. Been a lot of things that are going on here as I worked through some of the issues with making the tubing for the pilot's cage. You've watched the segment where I made this tube, which is now broken, and I identified that there's possibly an issue with all of the scrim that's on the carbon fiber, and I'm going to use an alternate cloth, and I've done that and some other samples also to do some experiments on strength and weight. Now this tube I broke on purpose to show you how the Kevlar protects the pilot in case of a crash. You'll see here that the carbon fiber has almost completely broken off. I think it's, yeah, completely gone. But the Kevlar is still kind of holding together. And I can touch the end of this and press on it real hard, and there's no problem here. If the Kevlar wasn't here, you'd have shards of carbon fiber stabbing me in the fingers, and I'd be off to get Band-Aids right now. But with the Kevlar on there, it's a non-issue. At worst, you might get some scrapes, you know, wouldn't be too bad. This tubing in a failure mode, in a crash, would definitely protect the pilot. This tube came in at 1.7 ounces per foot, and it's 3 layers plus a little bit more, and it's interleaved with the Kevlars I spoke about earlier. Now, I also talked about the unidirectional carbon fiber that I had from TAP Plastics that didn't have so much scrim on it. It made a really nice tube. This has got a nice finish on the outside. It was much easier to work with. The Kevlar stayed lined up with the carbon fiber quite well, and resin worked out nice. There's a few spots where the Kevlar didn't stay wetted out perfectly, but this tube is way more than strong enough for any of the components on the pilot's cage. 1.6 ounces per foot, so ever so slightly less weight than that one. Given the overall experience with this, I would have to say that this tube would be good to use. It's easy to make, and we can conclude that using unidirectional carbon fiber with a lot of scrim on it, it's a bad plan for making tubing. You have to have the unidirectional carbon fiber that has minimal scrim woven into the fibers as opposed to glued on the outside. You also see on here I have a piece of white vinyl, sticky back white vinyl on here. This is Orcal. This is the material that I'm going to use for coating the leading edge of the wing. I've run extended outdoor tests on this. This material is made for outdoor use, and it goes on really well on the D-tube on a smooth epoxy surface, very easy to apply, and resists UV completely and resists rain and everything else. It's great stuff. Not too expensive, and only weighs a little bit more than paint. This stuff's often used for, similar stuff is used in large sheets for coating cars. You see those cars that are gold and silver, and it's actually a vinyl that's been rubbed onto the surface. But I was wondering how it would go on to a peel ply surface, which is rough. And then with the ridges on here from the spiral wrapping of the various materials. And I was surprised. It actually went on quite well. A little bit more work, a little bit more rubbing to go as wrap it around, but it works. And I'm very pleased with it. It's going to protect the tubing from the sun. Even though it's covered in Kevlar, the stuff would heat up quite a bit in the sun, more so than we'd want. So I'm going to use this instead of paint. Paint would scuff. You have to sand it maybe, or clean it up somehow. You can repaint. This stuff will take its scrapes and its bumps, and it'll be okay. And you can get a hold of an edge and put some solvent in here, some like Goo Gone, and take it off. So maybe seasonally, during the winter, if you live in a cold climate, you sit inside and you redo your tubing, put new coating on it. But I think this is, for a home builder, this is a great answer. I think it's actually superior to paint. So I'm going to be using that on the tubing to keep the sun off. Then I made this piece of tubing. This tubing weighs 0.892 ounces per foot, really light. This is 2 layers of bidirectional plain weave carbon fiber cloth with 1 layer of Kevlar over the outside. Now, the reason that I did it that way is because if you're not interleaving the Kevlar, you need something to take the hoop stress loads. The Kevlar normally does that. This is all unidirectional. This is optimized for bending stiffness. All of the high strength materials are running lengthwise, and the hoop loads that keep the tubing round are carried by the Kevlar, which it's very good at, by the way. In this particular case, we only have 1 layer of Kevlar. It's not enough to carry those hoop stress loads and prevent buckling. So I use bidirectional cloth, which of course has fibers running this way to carry those hoop stress loads. Still at 2 layers thick, this is a little soft. I can squeeze it with my hands, and it will actually flex a little. If I point one end up at you here, you'll probably be able to see me do that. I can go like this and oval it out. That's not a good thing. That would promote local buckling, which would prompt a swift and catastrophic failure of the tube. That's how I actually broke this one. I put it on my knee, pull on the sides, and my knee actually pushes on the back side, causes a local buckle there, and then the tube fails. Local buckling, bad. On the plus side, bidirectional cloth does not give off as many needle-like shards as unidirectional. So the 1 layer of Kevlar over the outside is sufficient for pilot protection. And thereby, by not having to interleave, I can make tubing that's lighter, and this is actually fewer layers. So it's really a lot lighter. You got 1.6 ounces over here, 0.89 over here, almost half the weight. Full pilot's cage, 20 feet of tubing, not counting the big hoop up front. So you got 20 feet times 1/6, that's 20 ounces, another 12. So you got 32 ounces there. You're pushing on up close to 2.5 pounds. So here you got like 1.25 pounds. And it's hard to believe that this would, the whole pilot's cage, which I know you can only see part of it here, but the whole pilot's cage come in at 1.25 pounds, 1.33 pounds, and that would be amazing. And let me tell you, this tube is very strong in compression, very strong in bending. I actually lifted up my weight on this tube. I put one end on the ground, and I lifted myself up by pushing down on it, take my weight right off the ground. It'll take tremendous load. Maximum landing loads on this thing might be, even in a crash or a very hard landing with a lot of G's, you might put 150, 200 pounds vertically in one of these members. And this tube would easily take that load. Now here at the attachment points, there's going to be a little wood plug in here, and then a pultruded fiberglass piece of tubing through here that the bolt runs in, and that reinforces the area locally so we don't have failure at the attachment points. However, the local buckling is an issue. If you were to bump this on a landing, say with your helmet or your shoulder, you trip below, you bump into it, and it's going to collapse it. And as soon as you buckle it, the tubing's going to fail. And this is a problem that you run into with ultralight aircraft. Everywhere in the aircraft is local buckling. It is a structural phenomenon and failure mode that designers of these types of aircraft have to deal with all the time. And we use a variety of methods to prevent local buckling, usually bulkheads, ribs, stringers, anything to prevent the surface from buckling. All of those methods add weight. I could come in with some super high modulus cloth here, carbon fiber cloth, and that might do the trick, but then it'd get really expensive. I could use the tube just like this and cross my fingers. I don't know if that's a good plan. The pilot's not actually attached to the frame. As we mentioned before, he's attached to the wing, but the control stick will be here. And if for some reason this frame were to fail in flight, for some odd reason the pilot bumped into it on the side, flexed it, bent it, snapped it, then the controls aren't working, and then you're using that handy dandy backup system called the ballistic parachute, which we'd rather avoid if possible. So I think this tubing is a little too light because of the local buckling issue. I don't want to have to, if I can avoid it, I want to not design to resist local buckling loads, because that just makes the part heavier. And yeah, you're strong enough to resist local buckling, but now you're over strength for the other loads that you're carrying. And it seems kind of a waste to carry all that weight just to prevent the buckling. Now, you can look elsewhere on my site. You'll see where I took a piece of tubing and I poured urethane foam in here. It looks kind of silly. It foams over the top and so forth. That was an attempt to prevent local buckling on a single layer thickness tube. And I went and tested it and found out that as the urethane foam cures on the inside, you get a huge variation in density across the diameter of the tube. It really just did not work out well. So that's not an option. So we got that. So I thought, okay, let's just add one more layer of carbon fiber. This has 3 layers of carbon fiber, 1 layer of Kevlar. This is now plenty stiff in compression. I can still do it a little bit like this, but it's plenty strong. Rounded off 0.9 ounces per foot, 1.27. So this is 4/10 of an ounce heavier per foot, 20 feet, 4/10. So you got 8 ounces heavier. So we're carrying an extra ½ a pound to prevent local buckling. And for the whole pilot's cage, giving us the whole pilot's cage, I'm okay with that. I'll save 4 ounces somewhere else and 4 ounces somewhere else, and I got these 8 ounces covered. And still, I think that this tubing could be susceptible to local buckling due to ground handling boo-boos. Somebody steps on it, you hit a rock, somebody trips and falls and bumps their head into it. Things like that could happen. And the aircraft can't be a flying eggshell. It has to withstand some handling on the ground and so forth. So this is a compromise between absolute minimum weight and usability. Then, coming up next, you're going to see a video, fast forward video of me making these 2 tubes. These are my new concept of foam core sandwich panel tubing. There's actually a layer of fabric on the inside, then it is overwrapped with Aerex foam, about a 1/16 of an inch thick, and then a layer of cloth over the outside. So there's only 2 layers of cloth and a layer of foam. And let me tell you, this tube is really stiff. It takes a tremendous compressive force like this from my hands. I can grip it as hard as I want and not squeeze that. And this tube weighs the same as the one that's too flexible. So by using the sandwich panel methodology, I can provide the stiffness of the heavier tube for the weight of the more flexible tube. And nominally, that would seem like a swell idea, but I'm going to tell you in a moment why it's not. This one is fiberglass. I thought, you know, with a sandwich panel method, maybe you really don't need the carbon fiber for all that strength and stiffness. And I made one out of fiberglass. It'd be a lot cheaper. $17 to $20 a yard for the carbon fiber, $8 a yard for the fiberglass. So there's cost savings there. This one came in at 0.76 ounces per foot, even lighter. Feels like you're picking up paper with this thing. But this thing is really strong. It's a little bit flexible, a little bit more flexible than this in compression. And I think one more layer of fiberglass on this would bring it up to the weight of this tube, but even stiffer. It would end up stiffer than this tube. Same weight as this tube, but stiffer, much stiffer than this one. And I think that this could probably be the very best answer overall. Build the entire pilot's cage for a pound or less, excluding the fittings, which would be amazing. And nominally, I'd go ahead and do that. But actually, I don't have any more of the Aerex foam in stock. What I have right now is going into the wingtip panels, and I won't have any more coming for months, and I'd like to finish up the pilot's cage. And I do have quite a bit of carbon fiber cloth and Kevlar, and since I've already spent that money, I'm just going to make the tubing out of that. So the tubing is going to be made 3 layers carbon fiber cloth, and then 1 layer of Kevlar over the outside. These will be the uprights like this, and the horizontal ones will probably have 1 more layer. I'll probably run those up to the 1.6 ounce weight range, and they're actually going to be longer. It has to run from here back to here, and it has to extend back here. Here's the wheel that's going to go back here, so this tubing has to extend back, and from this fitting aft, I'll be tapering the wall thickness greater. I'm going to make the wall thickness thicker and thicker and thicker as we get back towards the wheel, so that it'll take, the wheel's cantilevered off the back here, and it's going to have to take quite a bit of bending loads as the wheel rolls around and bounces around on the ground. I don't plan on landing on this wheel. I don't plan on it. I'm not saying it won't happen, but I don't plan on it. I'm not going to design the structure to take really hard landing loads. If somebody wanted to land on this on a regular basis, they'd have to beef up the whole frame, probably add another pound to it approximately, in order to take those kind of loads, and I'm sure some people will do that. This is foam, got it on Amazon, nice and light, about as light as you can get for a wheel like this. It has metal bearings in it, which cause quite a bit of weight, and I wish I could get around them, but I can't. This is about the best that I could find commercially available. It's about the right size. So this would be good for rolling around on the ground. This with the skid up front, be able to just shove it around on the ground and be fine. Gets the cage up off the ground so I can get my hands underneath, get a grip on it, and should my old legs fail me and I trip on a landing, well, I got a wheel to land on and a skid, and things will probably be better that way. So a little bit of extra weight after this fitting to take the bending loads of the wheel. So there we go. I hope you stick around, watch the rest of this very lengthy video to see how these sandwich panel pieces of tubing are made. I think that in larger diameter tubing, up around 1.5 inches, 2 inches, is where this would really pay off. That these things could be phenomenally light and incredibly strong, and then you really only have to reinforce locally where fittings are. So pretty cool stuff. These are only the second and third samples of this stuff I've ever made, and with my tube production jig behind me, the process actually goes pretty quick, and you'll see that in the video coming up. I hope you enjoyed all this information. We're moving forward. I just got in some special material to help me move forward and begin building the whole center section of the wing. But first I'm going to finish up the tubing for the pilot's cage, and then I'm going to loop back around to the center section. Keep your eye out for an upcoming video on a review of the ribs that are going to go in the center section. I think that's a somewhat interesting topic. Also run into issues on how to save weight there and how to build just for the loads and keep the weight down so that this thing doesn't get too heavy. Right now it looks like I'm running in about 105, 110 pound range, so I'm working like I'll get out to get those last few pounds out of it. Want to get it down to the 100 pounds. So stay tuned. Hope you enjoyed. Wish me luck. Keep your fingers crossed. In the meantime, happy holidays. Fly safe, and I'll see you in the next video. Bye for now.
Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together. It's so beautiful, you and me. We meant to be in the great outdoors, forever free. Take a step back